Electric double-layer capacitor, Wikipedia Audio. Electric double-layer capacitors are electrochemical capacitors in which energy storage predominantly is achieved by double-layer capacitance. In the past, all electrochemical capacitors were called double-layer capacitors. Contemporary usage sees double-layer capacitors, together with pseudocapacitors, as part of a larger family of electrochemical capacitors called supercapacitors. They are also known as ultracapacitors. Supercapacitors do not have a conventional solid dielectric. The capacitance value of a supercapacitor is determined by two storage principles. Double-layer capacitance and pseudocapacitance both contribute inseparably to the total capacitance value of a supercapacitor. However, the ratio of the two can vary greatly, depending on the design of the electrodes and the composition of the electrolyte. Pseudocapacitance can increase the capacitance value by as much as a factor of 10 over that of the double layer by itself. Commercial double-layer capacitors. Supercapacitors are conventionally divided into three types, based on the design of the electrodes. However, because double-layer capacitance and pseudocapacitance both contribute inseparably to the total capacitance value of an electrochemical capacitor, a correct description of these capacitors only can be given under the generic term. Double-layer capacitance: electrostatic storage of the electrical energy achieved by separation of charge in a Helmholtz double layer at the interface between the surface of a conductor electrode and an electrolytic solution electrolyte. The separation of charge distance in a double layer is on the order of a few angstroms and is static in origin. Pseudocapacitance: electrochemical storage of the electrical energy, achieved by redox reactions, electrosorption, or intercalation on the surface of the electrode by specifically adsorbed ions, that results in a reversible Faradaic charge transfer on the electrode. In commercial double-layer capacitors, or, more specifically, EDLCs in which energy storage is predominantly achieved by double-layer capacitance, energy is stored by forming an electrical double layer of electrolyte ions on the surface of conductive electrodes. Since EDLCs are not limited by the electrochemical charge transfer kinetics of batteries, they can charge and discharge at a much higher rate, with lifetimes of more than 1 million cycles. The EDLC energy density is determined by operating voltage and the specific capacitance of the electrode/electrolyte system. The specific capacitance is related to the specific surface area accessible by the electrolyte, its interfacial double-layer capacitance, and the electrode material density. Commercial EDLCs are based on two symmetric electrodes impregnated with electrolytes comprising tetraethylammonium tetrafluoroborate salts in organic solvents. Current EDLCs containing organic electrolytes operate at 2.7 V and reach energy densities around 5 to 8 Wh/kg and 7 to 10 Wh/L. The specific capacitance is related to the specific surface area accessible by the electrolyte, its interfacial double-layer capacitance, and the electrode material density. Graphene-based platelets with mesoporous spacer material is a promising structure for increasing the SSA of the electrolyte. Double-layer capacitors with carbon electrodes or derivatives with much higher static double-layer capacitance than the Faradaic pseudocapacitance. Pseudocapacitors with electrodes made of metal oxides or conducting polymers with much higher Faradaic pseudocapacitance than the static double-layer capacitance. Hybrid capacitors: capacitors with special electrodes that exhibit both significant double-layer capacitance and pseudocapacitance, such as lithium-ion capacitors.